Hello, myself Naveen Kumar Saini. In the course Electromagnetic Field Theory, code KE301 in the lecture 7, today we are going to start in unit 2, electrostatic fields. So when we talk about the electrostatic field, the first point which come into our mind, charge, right? So the basic concept about the charge is when the charge is present into some space somewhere, it means there is some aura of that charge, and we call that aura is the electric field, right? So in that, first thing which come into the picture, that is a Coulomb's law, which is defining the force between the 2 point charges q and q2, and this is the relation for that charge for force between the two charges. F is equal to k times q1 q2 upon r square, and k is nothing but the proportionality constant, right? 1 upon 4 pi epsilon naught, right? So this is the formula which was experimentally proved by the Coulombs in the previous years when this charges combination come into the picture. So in that epsilon naught value, which is very much known to you, and this is the permittivity of the free space, and this value can be they can use it for the calculations of the this, if any kind of numerical units are important, farad per meter and the coulomb square per Newton meter square, and this value is 1 upon 36 pi 10 to the power minus 9 coulomb square Newton meter square or farad per meter. So it shows that when we have two charges placed somewhere in the space q1 and q2, and we want to find the force exerted on q2 due to q1, or we can say the force exert force exert on q1 due to q2, right? So for that purpose we have this formula, F12 is equal to q1 q2 upon 4 pi epsilon naught r square AR12. So this is the force exert on 2 due to the force q due to a charge q1, right? So force exert on 2 due to charge q1. So this point is very clear to all of you, and we have to specify the q2, that is these are position vector for q2 is r2 and position vector for q1 is r1. So it is representing here that r12 is equal to r2 minus r1, that is and r is equal to r12, right? So a, this is the unit vector, so this unit vector is representing as the vector r and divided by the result of magnitude of this vector. So in this we can also get this formula that F12 will be equal to F21. So this is the force exerted and the repulsion and the opposition of the charges, opposition, or the attraction or the repulsion of the charges will takes place when we have the two charges of equal magnitude, right? So which is given by the Newton's law. So here we have the principle of superposition. So in the previous case, when we want to find the charges between the forces between two charges, now we have the superposition theorem in which we have the more than two charges placed, and I want the force exert on one q charge due to the different charges. So if this is a formula which we are getting when we want it to find the force on q due to charge q1, due to charge q2, due to charge q, and so on. Just for example, if we have this charge and I have the different charges q1, q2, q3 and qn, okay, so this q1, so in this what I want to find the force exert on this particular charge due to these different charges. So for that one we use the principle of superposition. Okay, so this one is given by q into q1 because of this q1 and q. So q into q1 r minus r1 upon r minus r1 ka mod ka whole q plus q2 r minus r2 upon 4 pi epsilon naught r minus r2 की power 3 and so on. So this is the principle of superposition. So when we sum up, because this is the discrete charges which are distributed, this is not the continuous charges, so that is why we are using this one, discrete summation of the different charges, right? So in this way we can solve this type of problem. Electric field intensity, very simple, that is the force per unit charge is given by the electric field intensity. So F upon Q, which was again the unit for that is Newton per coulomb and the volt per meter. So in that, when we have the field, electric field intensity, if we want it at the distance r, due to the point charge which is located at the r dash distance, okay, so electric field will be q upon 4 pi epsilon naught r square ar, that is r minus r dash. So this r is the distance or the position vector for the charge q at which we want to calculate the electric field, and if the point any other charge is located at the r dash position vector, so we can get the electric field by the by this formula. And same here can be applied for the electric field in the superposition theorem, in that different charges are located at different positions, maybe n point charges are located at different positions, so r1, r2 up r1, and here we want to find the charge, we want to find the electric field at some particular instant or unit charge or test charge. So in that case, the formula will become q r minus r1 4 pi epsilon r minus r1, and this r minus r2, right? So this is the r minus r2, r minus rn, and so on. So by this we can find the electric field. The electric field due to continuous charge distribution. In the previous case, as we have discussed about the point charges, now we have the charge distributions. So charge distribution can be of different types. Maybe if we have a simple point charge, which we have discussed previously. Second, the line charge. If we have any line and charges are distributed uniformly on this line, we call this pen as the line charge. And surface charge, if we have any of the resistor or something like surface on which the charges are distributed uniformly, then we say this is the surface charge. And the volume charge, when we have the volume, in that volume the charges are uniformly distributed in that, then we call it as the volume charge density or the volume charge. So for that we have the formulas for the line charge, where the rho L into dl. So rho L is the line charge density. Okay, so in this total charge we can calculate by the formula rho L into dl. So line charge is there. Then we have surface charge, rho s is the surface charge density. So formula will become q is equal to rho s into ds. This is surface charge. Okay, so total, this this is the formula which is representing total charge present onto the particular line, particular surface, right, or the particular volume. So in that we have to require the volume charge density. This is the rho v is the volume charge density. When we multiply it with the dv, so total charge present into this given volume is we can calculate it by this, when we have the value of volume charge density. So similar to that we have the electric field. So this electric field, that is rho L dl upon 4 pi epsilon naught r square. So this is the line charge, surface charge, and the volume charge. Due to this all surfaces or the volume charge densities, we can find the electric field. Then one of the example we can take it here, when we want to find the line charge electric field at the particular point which is mentioned here due to the line charge. So this line charge is from A to B, right? So in that the q dq, as we have just simply said in the last class, in the last slide, where we just simply mentioned that q is equal to rho L into dl. So when we take the differentiation of this line, then we will get dq is equal to rho L dl, that is rho L into dz. Okay. So total charge we can find very easily if we have this one as the ZA and this is the ZB. So when we take this limitation from here, ZA to ZB into rho L into dz from here, okay, so we can take it here, right? So in this way we can find a total charge present onto this line. Okay, so for solving this situation, if we want to solve this problem, so what we required, so the things which we have, there is a total charge we can calculate from this formula, and we want this distance. So this distance, if we can get it, then we can solve the finding the electric field, right? So for that, this point is the x, y, z. This is a point P which we have, and I want the electric field at this point. So for that I want the distance r. So for getting this, simply this is a line. So we know how to solve this line problem. This is the x minus 0, because this is nothing but this is 0, 0 or some value we are taking as a z dash, right? So when we'll take this one, so this will be z minus 0, y minus 0, z minus 0, z minus z dash. So this equation will become like this one. So this is the value of r. Okay. So in again we can also see here that x ax plus y ay, this is nothing but the rho arrow in the cylindrical coordinate system, right? So this is in the cylindrical coordinate system. So we are simply writing this r is equal to rho arrow plus z minus z dash az. Take the magnitude of this. So when you take the magnitude, so this is like this, and here we can write the magnitude for this x square plus y square, that is rho square, and that is z minus z dash ka whole square, right? So when we want to find the electric field, so for that, as we have mentioned previously, that E is nothing but that is the 1 upon 4 pi epsilon naught r square, right? AR or the Q, right? So Q we are aware about that. Q we can find by the integration rho L into dl, but important point here is the R. If we can get the R, so things will be easy to understand. So this AR and R cube, R square, we can write it here. So AR is a unit vector, so this unit vector can be converted into the vector R divided by the mode of R. So this will become the R cube, and we just put all the value all together into this equation. So when you put it all together, then the expression which we are getting here, right? So this is very, very important expression which is to be solved now. So for that one, we can do the integration of that one. So very simple fashion, we can use this one, this portion as the rho sec alpha. Okay, so this is a simple integration which will help you to understand in this how to solve these integrations. Okay, so z dash, if we go for this z dash, so z dash is nothing but the complete section. If we go back, so this z dash, right? So this z dash will be what? This complete z minus this portion. So this portion is nothing but the rho is here, alpha is there, then rho tan alpha will give this expression, right? So this is the this will be the OT minus rho tan alpha, right? So just put all together, then dz dash, take the differentiation of that because we have to put the value here. So this is the expression. After solving all this, we will get this one, and now this is the finite line for the finite line electric field. This expression we are getting. Now if we want for infinite or semi-infinite lines, so we have to take B in the up maximum and A maximum downward. So in this case, the value of alpha 1 and alpha 2, which we can go through from this diagram, from the previous diagram, alpha 1 will be pi by 2 and alpha 2 will be minus pi by 2, right? So in this way, we just put all values in the previous expression. Then electric field due to the line charge will be rho L upon 2 pi epsilon naught rho into A rho. Second example of this one is surface charge. In that we can use any surface. Okay, so in that surface we are taking the simple elements. So from this element, what I want, my question is, I want to find the electric field at some point P, which is whose height is at h. Okay, so for that purpose I want to find the electric field here. So for this purpose I will take one of the segment on the surface, that is a ds. Okay, so ds is here. So what I require, I have to find this distance r from this point to this point P at which I want to find the electric field. So total charge on this surface we can find by this formula, rho s into ds. As I said, rho s is the line surface charge density and ds is the elemental area. Okay, so when we integrate this, then total charge we can find out from this formula, right? So we can see when we integrate it, the total charge can be calculated at this surface. Okay, so same method again we have to apply as we have discussed in the previous case, where formula which we have, dE at the particular point, that is equal to dq upon 4 pi epsilon naught r square AR, right? Same formula we have to apply, but the difference, what happened, difference will be occur when we have the total charge. So total charge in the line integral, we have to take the line charge density. When we are talking about a surface charge, then for that one we have to take the rho s ds, right? When we require the volume charge, so in place of dq we have to write the rho v into dv, right? I think this point is must be clear to all of you. Okay, so now again the main concern is here what we have R. So R we have to find. So how to find this R? So this is the R which we have to require. H is there, rho is there. Simply apply this A plus B is equal to C. So this vector phenomena, just simply apply it here. So this direction is AZ, this direction is A rho. Okay, so in this way, this is the A, this is B plus is equal to H. So when you rearrange all these things, then expression which we are getting like this: minus rho minus A rho plus H A Z. Okay, so magnitude is there. So put these things into this equation. So expression which we are getting like this, right? So this is the electric field at some distance h from the surface of the sheet. So when we integrate that with simple integration is there. There is no nothing tough here. So by using infinite sheet of the charge, then the electric field will be this much rho s upon 2 pi epsilon naught a n. So the difference you must know that rho s is the surface charge density in the on the sheet, right? And rho, which we have taken care of in the previous case, this rho is the in the cylindrical coordinate system, rho is the radial distance of the cylinder. So these rhos are, I mean, you have to differentiate it, right? Rho s is the surface charge density, and simple rho in the cylindrical coordinate system which we are using here, that is the this is your radial distance from the z axis for the cylinder, right? So when we have these two parallel sheets, and because we are very much aware about the capacitors, which we have the two sheets parallel to each other, and if we want to find the electric field in between these two capacitors, so these things, I mean, two capacitor obviously, so one will be positively charged, second will be negatively charged, and we want to electric field at this point in between the capacitor. So when we use this formula, so rho s is there because of the positive charge density, and this one is the minus rho s because of this negative charge density, right? So when we apply this, okay, so an is in this direction and minus an is in this direction, so we are taking the minus sign here. So when we add these two contents, then finally we will get the rho s upon epsilon naught a n. Okay, so electric flux density, that is D is equal to epsilon naught E, where when we multiply the relative, I mean the permittivity in free space with the electric field, then finally we got the electric flux density, which is the property which is defined when we have the any kind of medium. Okay, so flux density, which is defined D dot ds. Okay, so D dot ds, that is giving that is a flux which is passing through a closed surface. Some I mean, this is Gauss law or the Maxwell's equation, which is coming from here. So Gauss law is nothing but which is mentioning that electric total flux going out from the surface or the volume is equal to the total charge enclosed by the surface or the volume. Okay, so just apply this law, that is phi is equal to D dot ds. This is the total flux, and Q enclosed, this is the total charge in the given volume. Obviously this is the volume charge density. So when we combine these two, the equation will become here. And after this, when you apply the divergence theorem, so in the divergence theorem, as you are aware about the divergence theorem, that the divergence theorem relate the closed surface with the volume. So in this way we can write it by the divergence theorem, that D dot ds with the closed surface equal to del dot d into dv. So from here we have come to the conclusion about from these two equations that rho v will be equal to the del dot d. So this is the Maxwell's equation from where we will start the application of the Gauss law if time permits to us. Okay, so I hope this this section is very much clear to all of you. In the next section we will take more topics which can make you more understandable. Okay, thank you very much.